All right, let's make a start. So firstly, just to check, you are all expecting multivariate calculus. And I am, so this is good. I am Claire Blackman. You've already received a bunch of emails via Canvas from me. I try to communicate regularly because I feel like it helps. All right, so here we are. This is the first time I'm giving an in-person lecture in 2 years. It's terribly exciting, and I hope I remember how. No pressure. I think I've met quite a few of you in various contexts, but just for those of you that I haven't met yet, I joined MSP in January. I come from South Africa. My background, I did an undergrad in maths, physics, and astrophysics. Then I did a PhD in astrophysics. Then I took a break to go do opera singing for a while. Then I missed the maths. I really missed the maths. So I went back to university and I did a master's in maths and ended up teaching at University of Cape Town for a few years. And then ended up here. My focus is really, my focus is really maths that is useful for other people and teaching it in that way. In my heart of hearts, I am a pure mathematician and I just enjoy doing pure maths, but I realize that most people actually don't. So I'm not going to torture you with lots of pure maths as far as possible, and if I do go down that tangent, just kind of go, Claire, back away from the pure maths, we need the applications. Unless you like the pure maths, in which case, all good. Just a heads up, I am recording the lectures because, as I'm sure you know, there's kind of in an hour and a half, there's a lot of content, and I don't want you to feel like you have to just like get everything down so that you can't actually listen to the lecture. If you have any problems with the recording, I've got it facing me, so you shouldn't be involved. But if you have any problems, let me know, and I will make a plan. But I'm kind of hoping that this is an acceptable compromise. I will put the videos up once I've had a chance to kind of sort them out later this evening. Okay. All right. Any questions so far? So I thought we'd just take a few minutes, a very few minutes, to just trundle through the course outline to just make sure that there are no surprises. I've tried to keep it as comprehensive as possible. So we have 3 tutorial groups. I will be taking one of the tutorial groups, and Gabriel from Maestro will be taking 2 other ones. He's super experienced. He's tutored this course a bunch of times, especially with Ronald in previous incarnations. Yeah. So if you want to get hold of either of us, Gabriel mostly is going to be by email. You can get me via email. At the moment I'm 2.008, but I am moving offices when they give me a key for the new office, at which point I will let you know which office that is. What is this course all about? This course is to take you essentially through a lot of the physics a lot of the maths that you will need if you're going on with physics. There's also a lot of maths here that you will use if you do anything mathsy related that goes beyond basic calculus. So this is, but the kind of the focus of this course is going to be applying what we know to physics. I think it's quite important for you to know where I come from in my kind of thinking about teaching. Firstly, everybody can learn something. People learn at different paces though. For example, I'm quite a slow learner, but I'm sure that there are some of you who are super speedy, and there are people in between. But everyone can learn, and it's up to you to kind of figure out how you do that learning. I can help you, I can point in directions, but you're you. You got to do you. Maths is a tricky one. I say this with 20 years of teaching experience. The thing about maths is you have to really deeply understand new concepts. So there's a kind of a really deep learning involved, but there's also, you just have to practice it a bunch. It's a lot like if you want to become good at any sport or a musical instrument or anything like that, you have to have deep understanding of what it is that you're doing, but you also just have to put in the time, doing the push-ups, playing the scales, doing whatever. So that is something I really want to encourage you to think about as you go through this course, is consciously switching between these 2 ways of thinking about maths. On the one hand, the really deep, like getting to grips with like what is this tangent thing, okay, really getting to grips with it, and then just the routinized practice of integrating this line integral and doing it again and doing another one and doing another one until it becomes muscle memory. You need to do both of these things if you're going to really get the most out of this course. Partly because when you come across the maths in some other context, whether it's physics or you go on and do something complicated in biological sciences that's involving matrix algebra, it needs to almost be that your mind goes, oh, I've seen this before. And it's only going to be in that space if you've done it a bunch of times. Okay. So, before I carry on with that, the other thing that I will say is sometimes learning can be a little uncomfortable, particularly when it's something that you don't understand immediately. I'm guessing that many of you at school, maths was quite easy, at least up to a certain point, and you just got it, and then maybe you got to a point where suddenly you didn't get it anymore, and you were like, oh my god, what's happening? That oh my god, what's happening moment can be uncomfortable. It's okay though. It's a normal thing. Come on in.
Yeah, sorry, I just trying to find a seat. I'll just sit over.
Okay. Don't feel bad about being uncomfortable. It's kind of an important part. It's how you know you're learning something new. If you're completely comfortable the whole time you're at university, then honestly it seems like it's a bit of a waste of time, because you're probably never being challenged. So think of being uncomfortable and slightly nervous as a sign that you're getting your money's worth. That said, obviously if you're feeling panicky and nervous, that's not a great space to be doing maths in. So the flip side of that is learning to acknowledge, okay, I'm feeling nervous but a little uncomfortable. I'm going to take a few breaths. If you're me, eat a piece of chocolate, calm down, get yourself in the right headspace, and then do the maths. But the important thing that I want you to take out of all of this is don't just pretend that learning isn't about emotions, because it's totally about emotions. How you feel about a subject is what drives you to study it. And that feeling is a feeling. It's not a thinking, it's a feeling. So use your emotions, get in touch with them, be practical about it. I will give you as much feedback and much opportunities to get feedback on your learning as possible, because otherwise how are you going to know how you're doing? I don't know, okay? Likewise, I will elicit feedback from you because I can't adapt my teaching if I don't find out how things are going. And this is the first time I'm teaching, firstly, this course in my life, and secondly, a course at MSP, which is a very different environment to one that I've been in. So I will be asking for feedback. Please let me know so that we can actually make this as efficient and pleasurable for everybody as possible. I do take feedback seriously, and I will do what I can. Sometimes I will say, I'm sorry, I can't change that thing, but I will give you a reason. Okay? And finally, we're all human beings here. Let's acknowledge that and be kind to one another. I think we've all had a pretty tough couple of years. I don't know about you, but I'm actually quite tired. So yeah, let's be kind. And linked to that, which is also around the whole practicing thing, as I've said, to do maths, to learn maths, you have to practice. You kind of have to do it. So there are weekly quizzes, weekly online quizzes, and you will hand in one tutorial solution every week that will get graded. But I realize that life happens. You have other courses, you have other commitments, life happens. So as far as I'm concerned, any deadline is flexible for the online quizzes and the tutorial submission. Just let me know, set a new deadline, because all I want you to do is do the work. And I want you to do it when you're in a space in which you can actually do it practically and sensibly and to the best of your ability. So deadlines are flexible. Let me know if I need to extend a quiz deadline for you. I will almost certainly do it. But this is about you taking responsibility and making sure that you make the time to do the work, because that's kind of what has to happen. It just has to happen. Sorry. Okay. I I need to stop talking about this and do some maths. Okay, there's a whole schedule here, and it's all terribly exciting, and you can see what we're covering. Please get a copy of the textbook. 7th or 8th edition will do. The 10th edition is now out. You can spend a lot of money. It's very pretty. If you do, you should be aware that they've added in a new chapter 11. So it goes chapter 10, and then you would update all the numbers, anything, if you were looking at the 10th edition, 11 here would be 12 in the 10th edition, and so on. Okay, it's very shiny, but you know, I would get a second-hand copy. I'm waiting to hear about when the midterm is. I will let you know as soon as I know. In terms of how your final grade will be calculated, online quizzes, I will take just the straight average. There are 5 of them. That will count 15%. Tutorial submissions, there will be 6 of them. We will take a straight average. That will count 15%. Midterm somewhere in week 4, 30%, and the final exam 40%. I will give you more details on the format of the midterm and the final, but they will be in-person written. Yeah. I don't believe in memorization, so I will give you formulae and stuff like that. But there is stuff that you do need to kind of have in your head, which is why you should practice. As I've said, I am all about the extensions if you need it, but as a result of this, if you fail the course and you haven't submitted all the online quizzes and the weekly tutorial submissions, you're not guaranteed a resit. But if you've handed in, if you've made a valid attempt on everything, you get a resit and life goes on. Okay, that is my bit of being stern. Okay, you have to do the work. Study materials, we have a textbook. You will have seen I uploaded a set of lecture notes, which I'll be working from now. I will upload the annotated version as well, and I will try and do this like well before every lecture. Today was a bit last minute. Also, as I said, lecture videos. I'm hoping that this simple solution will work. If it doesn't, I'll try and do something a little more high-tech. The other thing that I will probably do is, and this will need feedback from you, I'm happy to do little videos of worked solutions of some of the more complicated problems and just post them. But for that, I'm going to need you to tell me which ones to do. So I will send out a call each week and say, hey, which problems would you like me to work through? And you should let me know. Okay. You can read through all of that. It's just some hints for learning maths. And then I won't go through this, but I've just put together a page for each of the lectures, what it's basically going to be talking about, and then the reading, just so that it's clear. So if a section is not mentioned here, then it's not in the course, it's not examinable. If a section is mentioned here, it is in the course, it is examinable. But I will try and give you a heads up as to which things are more to focus on than others. So I've given you a list of exercises. These are the bare minimum. This will make sure that you've at least done one example of every kind of thing that we do, but ideally you should be spending, I don't know, 4 or 5 hours a day just working through the textbook in my ideal world. Yeah.
Are there any differences in the exercises between the different editions?
Nope.
No?
I have checked. You're good to go. So the only thing to check is your chapter number. Yeah. Things that have a star are kind of, if you're feeling like a bit of a challenge. Things that are in bold will be covered hopefully in the tutorials. So here is also your tutorial schedule. All right, any questions about the general course? How it's running, things like that? Any issues with logging into WebWorks?
I've got one question about the quizzes.
Yep.
Somewhere else in the manual it also said you have an unlimited amount of attempts on the quiz.
Yes.
So I was wondering, does only your first attempt contribute to the grade?
Nope.
Your highest attempt?
I think it's, I will double check, I think it's your final
Okay.
attempt. Yeah. Basically, I want you to keep going until you get it right. So you should be able to get 15% of your final without problem.
Okay.
I just want you to work.
I don't know if anyone else had this problem, but I did it Saturday night, I did the quiz, but then every time, even once I had the correct answer, when I moved on to the next question and then went back to the previous one, everything was gone. So, I mean, I saw that you changed something, we updated something yesterday, I believe.
Okay.
Maybe it works now.
Yeah, it works now.
Works now?
Yeah, it works now.
Okay, if you wouldn't just check if it doesn't drop an email. I'm using a new provider for WebWorks, and there are some little changes, so I can just check that.
Yeah.
Yep. Okay. Other questions? All right. So just a general question from me. How are you feeling about heading into this course? Yeah?
Mixed feelings.
Mixed feelings.
Yeah.
Okay, that's reasonable and honest, thank you. Yeah. All right, then let us dive in. All right, so let's be a little clear about where I would like us to go with this course, and essentially why, the fundamental reason why we're doing this. So, nice maths for physics. That is a broad and general goal. Specifically, what we would like is to be able to completely understand what is going on in Maxwell's equations for electromagnetism. So by the end of this course, the goal is that you'll not look at this and go, well, that's Greek. But you will look at it and go, aha. So here we have the del of the electric field is some constant, and you will have a feel for what that means. You will know what these symbols mean, and you will know how to calculate. If I give you an electric field, you'll know how to calculate this thing, and then you'll understand what this means here with these funny little partial d's if you haven't met them already. And more than that, you might understand that this is a whole system of simultaneous differential equations. And for some situations, you might be able to solve them. For other situations, you'll need to take the course that I'm teaching in the next period, which is differential equations. So, yeah. This gives you kind of a basis from which you can build on further things. But hopefully, this is where we're aiming to get at, that this looks familiar and workable with, so that when you head into electromagnetism as a course, you have all the maths that you need to be able to solve these equations in different situations. Okay? For today, though, we're going to keep things a little bit basic. So one of the things about Maxwell's equations is that, firstly, they're dealing with the world in 3 dimensions, or 4 if you include time. And a lot of the calculus that you've been doing is just calculus of one variable. So you've got an x and a y. And that's not useful if what in fact you need to model the system is an x and a y and a z and a t. So what we need to do is extend the ideas that we've got already from years and years of schooling into doing things in 3 dimensions. So today we just start off a little bit with analytic geometry in mostly 3D, but in fact it gives us the basis for going to n dimensions, which is useful. So just talking about how we actually describe things in 3D, which is going to be a recap for a lot of you. I'm going to talk about vectors. Can I just have a show of hands who's done something involving vectors? Okay. Anyone, like, what is a vector? Anyone not done vectors? That's okay. Okay, so we're going to skim through that. Cross product is just an aspect of vectors. It's something you can do with them when you're bored. Then we're going to talk about planes and lines. Obviously, in 2 dimensions, you've been dealing with functions a lot. You've been dealing with lines, straight lines, curvy lines, you name it. We need to be able to do the same thing when we're in 3 dimensions. But not only do we have lines in 3 dimensions, now suddenly we can have planes, and we can have surfaces. So we need to talk a little bit about how we handle those things. So we've got planes and lines, and we're going to talk about some surfaces, not all surfaces, quadric surfaces, which is kind of the equivalent to thinking about second order equations like quadratic equations in 2D. So it's kind of, keep in mind that everything we're doing, you already have an intuition in 2 dimensions. Now we're just kind of generalizing it a little bit. And I will keep trying to bring that there. Then we're going to take our newly acquired knowledge of vectors. And you've dealt a lot with functions. a function taking in a number and spitting out a number. But a function doesn't have to just involve numbers. You could, for example, take in a number and spit out a vector. No reason why you can't do that. All a function does is takes in one thing and spits out another thing. So we're going to talk a little bit about vector functions. So that's a function which will take in a single number and then spit out a vector for you, and how we deal with those. Yep.
Just a quick question, can it work the other way around as well? Well, it takes a vector and takes out a vector.
Absolutely. And in fact, that is lecture 2.
Oh, okay.
So we're going to look at all kinds of combinations. So the important thing about a function is basically that it takes in actually as much as you want, but it spits out one thing. But more than that, we don't care. Okay, so it can spit out a vector, it can spit out a scalar, it can spit out a matrix if you feel like it. Yeah. All right, so we're going to talk about vector functions, and then we're going to think a little bit more about curves in space, because it's a little, because we're dealing in 3 dimensions, there's a lot more to thinking about a curve than there is if you're just looking on a plane in 2 dimensions. So we're going to talk a little bit about parameterizations. Phew. Okay, so there's quite a lot to go. Questions? All right, so quick recap. So just to clarify what it is that we're talking about, what is analytic geometry? It's all the kind of algebra and methods that you need in order to solve problems in geometry, to solve problems in space. In 3 dimensions, length, width, breadth, but more generally in n dimensions, it's just they're harder to draw. So you've seen this a lot already in your life. But just to clarify, if we're in 2 dimensions and we've got a point somewhere, we put together a set of axes, and for the moment we're going to be using Cartesian axes, so things at right angles, nothing fancy. And there is a way in which you can calculate the distance from the origin to any point, which you all know and love based on Pythagoras. Hurrah! Okay? And in fact, if you have 2 points, you can do the same thing. Nothing particularly exciting here. Now we go into 3 dimensions, and this is where I will be using textbook drawings sometimes because it's hard to draw well in 3D. The thing to think about here is we have now 3 axes instead of 2, and this one over here we are imagining coming out of the board towards us, but obviously that would be tricky to draw. Now if you think about it, there are many different ways that you could put together 3 axes. The standard one that gets used for no particular reason except that it has become the standard is what's called a right-hand rule, and you might have learned different, like everyone has different ways of using their right hand to show a right-hand set of axes. But the way to tell that axes are following a right-hand rule, the way I learned, was if you put your, do I remember? I'm going to curl my fingers towards the y-axis from the x-axis, and then my thumb points in the direction of the z-axis. If I had a left-hand rule, then what would happen was the z-axis would be increasing down. If you don't care about this, that's also fine. The main thing to notice here is that the way that I will usually draw these axes is like this, with x coming out of the board, z going up, and y here. So we have annoyingly changed everything around from how you're used to in 2 dimensions when you have x and y like that. But if you move into a different country, or sometimes into different disciplines, they use different conventions. Just, sorry, you're going to have to get used to it. So we have 4 quadrants in 2 dimensions. If you've got a Cartesian coordinate system, now you can imagine if we've got our coordinate planes chopping up, we've got 3 coordinate planes, we end up with 8 octants. So we divide our space up into 2 with the first plane, 4 with the second plane, and then 8 with the third plane. And there are just some pictures to help you think about it. So it shouldn't be any surprise that when we're finding the coordinates and distances in 3D, we use exactly the same techniques that we used in 2D. It's just now we've got three things to think about. So if we have some point, so I am imagining that that point is actually sitting out here somewhere. So it has an x coordinate and a y coordinate and a z coordinate, and I want to find the distance of it from the origin. I can kind of do an extended Pythagoras-y thing, and I end up with something that looks very familiar. I'm going to have the root of x squared plus y squared plus z squared. Okay, you can check for yourself. You can bounce projections around and do it, but I'm not going to go into too much. And obviously, just as we saw in 2 dimensions, you can find the distance between 2 points. Just so that you're feeling completely comfortable with this for homework, show that if you've got 2 points in 3 space, that's the distance between them. Okay, so now we've talked about the space, and now we need to fill it with stuff. The stuff we're going to fill it with is lines and vectors and surfaces. So just to be clear, when we talk about an equation or an inequality, it defines a set of points which make that equation or that inequality true. So all an equation really is a way of defining a subset of the space in which you're working. Similarly, an inequality is just a way of kind of defining some subspace. And what that subspace looks like obviously depends on the equation or the inequality. So we're used to seeing equations in 2D. So if we have, for example, the line y is equal to 3, that equation just says of all the spaces in 2D, of all the points in 2D, the only ones we're interested in are the ones that happen to have a y coordinate equal to 3. So we've got a little subspace coming out of there. We can also have circles, but again, that's just a set of points. If we do something similar, so we just have a single equation, but now we're in 3 dimensions, then usually what we end up with is a surface. So the kind of 3D analog to a line is a surface. And we'll talk about these a little bit more, but just to give you some examples, for example, here is z equals 3. So compare that with y equal to 3 up there, which gave us a line. Now we're in 3 dimensions. When we just set one of our variables equal to a constant, we get a surface. Similarly, if I now take something that looks a lot like x squared plus y squared equals 1, but now we're in 3 dimensions, I end up with a cylinder, because this says give me all the points for which it is true that x squared plus y squared equals 1. Well, we don't have any information about z, so any x and y for which this is true and any z will work, and that gives us a cylinder. Yeah.
Then don't we need to adapt our original function to include z?
No. So well, what you need to do is specify what your what space you're working in. So here we would say, well, we're in 3 space. So, and our equation is this. Therefore, we haven't said anything about z, so z has no requirements.
Oh,
It can be anything. So if you have a situation where a variable isn't mentioned, that means it's free. If you want it to be 100% like super clear, you could do something like add and z is an element of real numbers. And that makes it explicit that z is being included. With that. Okay. All right, so pausing before then, any questions so far? All right, on to vectors. So before we hit vectors, just clarifying, a scalar is a quantity that only has a number, or a magnitude. You should be very familiar with these things like temperature, speed, distance, area, mass. All of these, it's just a number. It might have a unit attached, but it's just a number. On the other hand, as you've no doubt discovered by now, sometimes it's useful to be able to have a concept that enables us to describe things that have both a direction and a magnitude. And in order to do that, we introduce the idea of vectors. So a vector is simply a quantity which has 2 things attached to it, a direction and a magnitude. So in order to make it clear, because often we'll be using scalars and vectors together, to make it clear which one we're talking about, we use different notation. So when I'm referring to something as a vector, you'll usually see that I put a little like arrowy thing over it. Textbooks often boldface it, but that's hard to do if you're writing. And you'll see there are some little specific other notations that we'll come to as we go along. But generally speaking, when I'm talking about a vector, I've just got the little thingy like that. We show vectors graphically as arrows because this makes sense, because then we can get the direction from the direction the arrow points, and we can get the magnitude from the length of the arrow. Kind of a tricksy thing to remember about vectors is they don't have a fixed starting point. A vector is simply a direction and a magnitude. So if you look at these two bunnies over here, these are actually the same vector because they have the same length and the same direction. It's just they're starting in different places. And this is one of the things to kind of keep in mind with vectors. You can move them to start wherever you want that is most convenient. So when we add vectors, we might want to move our vector to think about it in one place, but when we're doing dot products and things, we'll move them elsewhere. Linked to that is this idea that actually a vector isn't a single thing, it's a whole family of things. So really, what a vector is this one and all the other copies of this one starting at all the different places that go the same direction, the same magnitude. And the way I think that is useful to think about it is you're used to dealing with fractions. A half and 2/4 and 4/8, they are all the same fraction, but they're different representations of the same fraction. And just like if you want to add a half and a quarter, then you'll probably use 2/4 as the version of a half that will make it easiest to do that addition. But if you were going to add a half plus an eighth, you would use a different version of a half. So when it comes to vectors, you can use different versions of the same vector for what you want to do. Maybe? Okay, we'll keep going. Okay, so these are mathematical thingies that we've just developed. And because they're mathematical thingies, we want to be able to work, combine them, do stuff with them, maybe get them interacting with scalars. So we need all the algebra for that. Adding vectors should be vaguely familiar. So suppose we want to think about a particle that moves from some point A to point B and then from B to C, and we want to find its final displacement. Well, its initial displacement is AB, then it does BC, and our result is here. So if we're adding vectors together, we kind of take our first one and then we move our second one to have its tail where the first one ended, and we see where we end up. This should be familiar? Yes? Yeah. Okay. All right, so I'm not going to ask you to do this. Maybe check through at home just so that you're happy. Just draw the little diagram of what you get when you add u plus v. And also check for yourself that if you add v plus u, you end up with the same resulting vector. Linked to this idea, if we have one vector a and we want to go a plus a plus a, well, what we end up with then is really 3 times a. We end up with a vector that is 3 times the length of the original vector a. And now suddenly we've moved into the realm of multiplying our vectors by scalars. So now suddenly we're taking our scalars, which we know and love, and our vectors, which we've just learned to love, and we're combining these two different mathematical objects. So scalars help us scale things. So if I want the vector, so I've got a vector v, if I want the vector that is in the opposite direction but has the same magnitude, I can just times it by -1. Very nice. Okay, I don't have to define some new vector, and so on. Okay. All right, so let's get into the maths of describing vectors. Again, depending on the discipline that you're in and sometimes the country, slightly different notation will be used. I'm sorry about that. Okay, so we're going to start by saying we are thinking of our vectors as happening at the moment in Cartesian 3 space, that we described a little bit earlier. And we're going to start out by identifying 3 special vectors, which we call the standard basis vectors, and they are these jobbies over here. They are I hat, is this little one, which is 1 unit in the x direction, j hat, which is 1 unit in the y direction, and k hat, which is 1 unit in the z direction. And the reason that I've got little hats on them rather than the arrows is because they are unit vectors. They are of length 1. And so as you see, whenever we calculate a vector that has length 1, and we specifically want it to have length 1, we'll call it a unit vector and we'll put a hat on it so that we know. Okay. All right. So now we have a new way that we can use to describe a point in 3 space. Previously we just had to give the coordinates, but now we can actually use a vector and say, if you start at the origin and you follow this vector, you will end up at your point. So we end up with notation here. We have what is called the position vector of this point P, and we will write that there are 2 sets of notations. We write it either with square brackets like this, so that it looks like a point, but it's not a point because it's got square bits. So this is, I want the vector that goes x units in the x direction, y units in the y direction, z units in the z direction. Or we can use what we've talked about with scalar multiplication and vector addition to create a new vector by saying, all right, how do I get to point P? So what is the vector r that will get me to point P? Well, if I go x units times my little I hat, and then I go y units times my little j hat, and I go z units times my little k hat, I will get to that point. Okay. This is not sacrosanct, and you will see that there are different basis vectors that you can use. And the further you go in physics, you will use different basis vectors. For example, you might decide, actually, Cartesian coordinates are not so great, I want to use spherical coordinates. And then you will, for example, use r and theta and phi. So you'll be using angles. But you will always need, if you're in 3 dimensions, you're going to need 3 kind of descriptory things that are independent. Okay. Okay. So the joyful thing about having now put things in a format like this is if you want to add vectors, if I've got a vector 1, 2, 3 and -1, -1, -1, and I want to add them, I just add corresponding components. We don't need to do this example, do we? Okay. The thing you do need to remember is this is a new kind of addition. Okay, this is an addition of vectors. It's not an addition of scalars. So technically speaking, we should actually use a different symbol, not the plus sign, just to remind us that this is different. So things that you would need to check is, does this commute? Is a plus b the same as b plus a? Is it?
Yeah.
Yeah, thank goodness. Okay, so that's fine. All right. But that is the kind of first heads up with working with vectors. Just because we use the same notation, we use multiplication and addition, those are different operations. So you should check that they behave the way you want them to. And sometimes we're going to find that they don't. So just kind of have a little kind of mental note, like, that's vector addition, not normal addition. Okay, and you can have a look through these. Just make sure that you're happy with these properties. This is giving you everything you need to know about addition of vectors and including scalars. One of the things to notice, just like we have 0 is an important scalar. If you add 0 to anything, you just get the thing back. The good news is you have a 0 vector, which if you add to any other vector, will give you that vector back. I will usually write that as 0 to make it explicit, but that's not a scalar. That is an actual vector in harmonic components. Okay?
Quick
Yeah.
question.
Yeah.
Then what's the use of having a 0 vector if it's the same thing as just adding 0? Or
I mean, what's the use of having a 0 in a scalar? I mean, in scalar, you need to have a thing that represents 0. And you'll actually see it coming up later. It plays exactly the same role as the 0 number.
You can't just add a scalar to a vector. It's
Yeah.
like-
Oh, was that
it's
what you're
like-
asking? Sorry.
Yeah, I was just asking why we need to differentiate it. Why we if it's the same thing as just
Because
adding 0.
because you can't add apples and pears.
Yeah.
Yeah.
That
Sorry, I
answers my
misunderstood. Yeah.
question.
Okay, so two kinds of multiplication for vectors, which hopefully you've seen before. The first one called dot product or scalar product, called the dot because we use a dot to represent it, called the scalar product because when you do it, you end up with a scalar. So this is one of the first weirdnesses. Now we're working with vectors and scalars. You can have operations which will take in a bunch of vectors and spit out a scalar. So this is our first example here. Here you take two vectors, but what you end up with is just a number. How do you do it? I've got my vector A, I've got my vector B, and what I do is I multiply the first coordinates of A and B, and I add that to the sum of the second coordinates, and I add it to the sum of the third coordinates, and I end up with just a number. Everyone good with? Yep. And this works like multiplication of scalars in that it commutes. So I can do A dot B or B dot A, and you can see you're going to end up with the same number. So it's great. The only thing that's weird about it is the fact that you're putting in vectors and you're getting out a scalar. But it turns out to be useful. Okay, and there are some products, some properties for you to have a look at. One of the most useful things, which we'll come to in a moment, is that the dot product gives us a way of checking if two vectors are at right angles to each other. And you'll see this coming up again and again and again. You want to find out whether one vector has some component in the direction of another. You just check, you take the dot product. This comes out of the fact that if we've got an angle of theta between two vectors and we take the dot product is the size of A times the size of B cosine the angle between them. So if you think about this, if I've got two vectors, let's have an A and a B like that, and a right angle over there. If I calculate my dot product, what is the cosine of 90 degrees?
0.
And our dot product is 0, and therefore we know that they're 90 degrees. So, I mean, for me, you will use the dot product in other contexts, but as it's kind of, as a quick tool, it just gets used so much for checking if two vectors are at right angles to each other. All right, so that was the first way of multiplying. So that was take two vectors, get a scalar. Now we have what's called the cross product, or the vector product, called cross because we use a cross like good old times back in the day when you were learning multiplication, to differentiate it from the dot. And it's called the vector product because you end up with a vector. So you put in two vectors, you get out a vector, which might seem more natural. The dot product, the cross product is a little bit weird because it's only defined in 3 space. You can't find, if you've got two-dimensional vectors, you can't do the cross product. If you've got 4-dimensional vectors, you can't do the cross product as it's defined here. It's only defined for vectors in 3 dimensions. The other slightly strange thing about it is you'll have your two vectors that you're going to cross product, maybe here and here, and the vector that the resulting vector that you get is at right angles to those two, to both of them, which is going to be a useful property in a moment. Calculating the cross product is a pain. Yep.
Yeah, I'm just asking this out of curiosity. Is the cross product defined in 5D?
No,
dimension?
not like this. So there is a kind of a generalization which is called the wedge product, but it's slightly different.
Okay.
And you don't end up with a vector, you end up with I think a tangent plane or something. But it's kind of like it, sort of. Yeah, it's just three space.
Okay.
Yeah. Okay, how do you calculate these bunnies? Well, you can learn the formula. These ones are a bit weird. Okay, so I've got my vector u with its 3 components, my vector v with its 3 components, and now I need to end up with another vector that has 3 components. The I component only uses the y and z components, so I get u2 v3 minus u3 v2, and so on and so on. You've hopefully seen this before. Yes? Okay, so I'm not going to go into laborious practice here. I don't know who's done linear algebra here. Huzzah! Okay, well then you can just use determinants. You've done determinants? Yes, okay, great. So an easier way to do this is if you've got u cross v, set up that matrix over there, find the determinant. Okay, this is a routinized thing you just need to learn to do. You will need to, I promise to ask you a question involving calculating the cross product. Please learn how to do it so that you can get easy marks. So the important thing to remember about cross products is they don't commute. Okay, so this is important. Okay, these bunnies, this product does not behave like the products you know and love that we've seen so far. It almost commutes in the sense that if you've got A cross B and you look at B cross A, they're going to have the same magnitude, but they point in exactly opposite directions. So they anti-commute. And that's useful in some contexts. But just remember, order matters in the cross product. So for all these examples that I'm working through, well, not actually working through, I will fill in my notes so that you can go through and check that you're happy calculating all these things. Okay. All right, why do we care about the cross product? Well, it turns out to be quite useful. The one thing is that we often want to find, if we have 2 vectors, we want to find a vector that is at right angles to both of them. And the cross product does that for us. So now let's put this all together. What does this line really say? Well, this says whatever vector I get out of my cross product, if I dot it with one of my original bunnies that I have over here, I get 0. So this tells me that my cross product result is orthogonal to the u, and it's also orthogonal to the v. So here you see right away one of the uses of our dot product to check that 2 things are orthogonal. We also have that there is a link, so you'll remember that when we found the dot product, we had magnitude, it's the magnitude of each of these times cosine of theta. A similar thing happening over here with the cross product, so you can also use this for finding angles. And there's more going on here that if you do more physics, we can look into. But for the moment, these are properties that are useful about the cross product. Yeah?
How does u cross v change in the second formula if you swap u and v? It doesn't like u do the same.
So if I did v cross u,
Yeah.
yes, wait, sorry, yes, so it'll give you exactly the same thing.
Yes, but isn't u cross v different than v cross u?
So u cross v is the same magnitude in the opposite direction.
Okay.
But notice that I'm taking magnitude here. So all I'm caring about is the magnitude.
Okay.
So that loses our direction information. Yeah. Right, quick check-in. Will winter vectors? Give me a show of hands. I'm totally good with this. I need to do a little bit more work. I have no idea what you're talking about up to now. Okay, we have a few of this, but basically, okay, great. Phew. Okay. So let's just take a moment. Put your pens, pencils down. If you feel comfortable, close your eyes. Otherwise, just like look somewhere kind of neutral. I'm not going to switch this off because then bad things happen. And we're just going to take a couple of breaths because I just downloaded a lot of information. Okay. So what I'd like you to do is just let your brain kind of relax for a moment. Take your attention to your breath. And see if you can notice how your body changes as you breathe in and breathe out. So just give your mind and your soul a moment to just relax and just think about breathing. Just watch yourself breathe. If you find that your mind's wandered off, that's fine. Notice where it went and then bring it back to your breath. Just follow your breath. 2 more breaths. And bring your attention back to the classroom. And take a moment to just write down what you get if you find the magnitude of the dot product. Just think back. We talked about it. What I want to know is, what is this? And I don't actually even really need, you don't need those. What can you remember about that? Write down anything. Yeah.
Well, we can go the way, we can say it's A1, B1 plus A2, B2 plus...
Okay, that's great. Yeah, so we've got
plus A3, C3.
Mhm.
And B4, yeah.
okay, someone else wanna?
I had A, B equals BA.
Okay, and you remembered that A dot B is equal to B dot A. Anything else?
I mean, they're the same as the magnitude of both separately multiplied by the angle between them.
Okay, so we've got, this is also equal to A, B, and it's a cosine.
Yeah.
Nice. So, this is not about memorizing stuff. This is about giving your brain a chance to actually just recall stuff. So I suggest when you go back and go over this lecture, you take each little section, read through it, close the book, and then see what you can remember. Write it all down. Go back, check, and if there's stuff that you forgot, rinse, repeat. Okay. Yeah? Alright, so on to the next section. Right, so so far we've looked at how we describe points in 3 space. We've introduced a new way of doing that using vectors. Now we need to be able to talk about sets of points in 3 space, which is essentially planes and lines. So if you think about everything you know about straight lines in 2 dimensions, which is a lot, you've been doing these things a lot, what you know is that if I hand you a point on a plane and a direction, you know that there's only one line that's going to go through that point in that direction, and you can find the equation of that line. Yes? Yeah. We can do the same thing in 3 space. So if you think about it, now we're in 3 space. If I give you a point and I give you some direction, there's only one line which will go through that point in this direction. It'll have to do something like that. So essentially we're going to be using a vector to give us our slope in the way that we used an M, or whatever you called it, when you did gradients and slopes in 2 dimensions. So now we're just using a vector to give us our direction, and we need a point. So the idea is that we have our point P, and we have some vector giving us a direction, and what we're going to do is we're going to imagine that we're taking that vector to start at our point P, and then we just take all the possible scaled versions of that vector, and that's going to give us all the points on the line. So there's my vector V, and I'm going to have a half V, and I'm going to have 1.5 V, and 3V, and I'm going to go in the opposite direction too, so bunches of scaled versions of V, and suddenly I can generate all the points on my line. What does that look like mathematically? This says that if I give you the position vector of a point and some direction, then the line going through that point is the set of all points that you get if you start at your initial point and take some scaled version of your vector from that point. Does that make sense? So, things to note. Our t here is running from -infinity to infinity, so we're taking all possible scaled versions of v and adding it to our position vector. So we are using the fact that we can multiply vectors by scalars here. This form of a line is called the vector parametric equation, and think of it like the good old y equals mx plus c that you know and love. Because what you've really got here is y is equal to c plus, I just change things around. This is acting as your constant, it's your starting point. Your x that you know in y equals mx plus c is the thing that varies. Here we're using a t, because we could. And your slope in y equals mx plus c is, the analogy is this direction vector here. So you can use a lot of your intuition that you have about lines in 2 dimensions when you're in 3. So that's just a picture that we've already seen before. Now, we have lots of, so one of the things you'll notice when we're dealing with vectors is we have quite a few different forms that equations can take. So we just saw the vector form, but sometimes it might be useful to divide this up into what is called the scalar parametric equations. Here, all I'm really doing is I'm looking at each component from my original equation over here. So remember that my r here is an x and a y and a z, and my r0 is an x naught, a y naught, and a z naught, and I've got a t, and my v is a, I can't remember what I called v, ABC. So all I'm doing when I split this up into these equations here is I pull out the x components, and they have to satisfy this equation, y have to satisfy that, and so on. And now this really highlights how much this is like the equation of line, because here I've got y is equal to some constant plus some constant times a variable. Okay. Sometimes it's useful to do this. So these are our scalar parametric equations. You might look at that and say, that's displeasing because I have 4 variables and 3 equations. So I should be able to neaten things up. And in fact, you can neaten things up. If you solve for t in each of those, you could end up with these equations over here, which are called standard form. So no t. So some things to practice will be just working with the different forms, but all of these forms give you the equation of a straight line. So understanding that if you want to know what point I mean, obviously this line goes to lots of points, but you can pick a single point, it goes to the point x naught, y naught, z naught. If you want to know the direction that it goes in the direction A, B, C. So you can pull out your information the same way that you can from y equals mx plus c from these equations. Okay. Vector functions of one variable. So as I mentioned at the start, you've probably been thinking you maybe met function machines when you were a lot younger. The idea was that you put a number in from the domain, the function machine does something and it spits out a number from the range. In the previous calculus class, you probably got a slightly more sophisticated definition of what it is to be a function. A function, it's a rule, which is, we've not defined what a rule is, but okay. It's a rule that takes each element in a set D, which is our domain, and assigns it to exactly one element in a set E. So the key thing here is that you have an input set and an output set and a rule that takes something from here to exactly one thing in here. So you're not allowed to have this going to something different there. Okay, anything else goes. The useful thing about this more general idea of a function is we haven't specified what you can use as your inputs and your outputs. So what we're going to start by doing is now, instead of thinking of both our inputs and outputs as numbers, we're going to think about our input as a number and our output as a vector. And to make this a little more concrete, what you want to think about what we're describing is a particle moving through space over time. So what you're wanting to do is your input is going to be the time, and the output is going to be where the particle is at that particular time. So our input is a scalar, and our output is a vector, a position vector. So this is the kind of mental picture that you want to have. So here's our particle zooming along, and at any particular time, you put in the time, and your function is going to spit out where our particle is. Okay. Now we're doing this so that you have an intuition, but we will generalize this to just say, well, we're going to have a function where you put in a number and you get out a vector. And we don't put the interpretation of time and position. But for the moment, so that you can build this up in your head, think about a particle moving through space. So the things to notice, we've got our particle moving through 3 space. Its x-coordinate is a function of time, its y-coordinate is a function of time, and its z-coordinate is a function of time. And we can pull those all together into this vector equation here, which says my position as a function of time is wherever I am in the x direction at time t, plus wherever I am in the y direction, plus wherever I am in the z direction. Okay. And because we're thinking about time, we're thinking time is increasing, so as time increases, we follow our curve. And now, suddenly, we can start to think about things like velocity and acceleration. So here's my curve that my particle is moving along, and I'm thinking about at a particular time, t. I've got a position here, and if I think a little bit later, delta t later, my particle will have moved to here. And this should be starting to look hauntingly familiar. You might even be twitching already. You can feel the limits coming, can't you? Okay, so in a little time delta t, we've gone from here to here. So my average velocity, which is the change in my velocity, must be my change in displacement over my change in time. And then we do the calculus thing by making some assumptions that our curve is nice and smooth, which I'm not going to go into a lot of detail about. But basically we make our delta t really, really small, and suddenly we have derivatives. Okay, so we're taking my average velocity, just like you did in calculus 1, and I'm letting delta t go to 0, get really, really small, and what I end up with is that my velocity is the derivative of my displacement, which should be a relief. It would be weird if it wasn't. Okay, but all that we've really done here is we've turned this into a vector equation over here. What is this thing? Okay, I wrote this out for you so that you don't have to. All right, you never have to write this out, but just to make it explicit. So I've expanded what it was that we did when we took those limits. Well, my original displacement was, my little change in displacement was this thing here, which I let the limit of delta t go to 0. And so what I actually end up with, my velocity is the derivative of my scalar function in my x direction, my scalar function in my y direction, and my scalar function in my z. Pause for a moment, look at this, and ask me any questions. So I'm sweeping quite a lot under the rug here, let's be clear. Obviously, if you have some like weird, jaggedy particle motion, just like in 2 dimensions where you can't differentiate something like this at the point, if my particle is doing some weird stuff, there will be points I can't differentiate it. So I'm kind of sweeping that under the rug and saying, I'm just assuming that we live in a lovely world where our particle just gently does like nice curvy stuff that I can differentiate everywhere. And when we have that delightful, happy world, then it turns out that the velocity of our particle is just, as you might expect, the speed in the x direction, and the speed in the y, and the speed in the z. It's divided up into components. Okay. And your velocity in 3 dimensions does all the things that you would hope it would. Your velocity is tangent to your curve, just like in 2 dimensions, your velocity is tangent to your curve, so that's good. Okay. Our speed is given by the magnitude of our velocity. So everything we've used so far, you can use to calculate the speed. And without spending any more time, if you want acceleration, you just take the derivative with respect to time again per component, and you're done. Okay. So here is one for you to practice. So the textbook, and this is why I'm using it, uses this notation here. For myself, I would usually prefer to write this just in component form like this. Oops. That's the format I prefer. I find it quicker. And then when you want to find the velocity, you just differentiate each component with respect to time. Okay. And the thing to think about here is not only that you need to find velocity, speed, and acceleration, but also describe the motion. What is this particle doing? What shape, what curve is it tracing out in space-time? And I'm sure you're delighted to know that there are more differentiation rules. I'm writing them down. I will give them to you in a test or exam, but they're exactly what you would expect. So the thing to take out of this is to realize that we're now combining vectors and scalars, so you need to think about how you would differentiate. So for example, I think this one is the most relevant thing over here. What have we got here? This is a scalar function. This is a 2 that you're used to. Okay, so it's a function where you put in a number, you get out a number. This is a vector. Firstly, is that legal? Can I do that? Yeah, we're allowed to multiply vectors by scalars, and nobody said that the scalars had to stay constant. Okay, so that's fine. Okay, that's. But now, if you want to think about what this has to look like, it takes a little while. going to need to do a chain rule type thing, you've really got a something multiplied by a something. Think about it. You're going to have the derivative of this times that plus the this times the derivative of that. So that is kind of an extension of the chain rule. So it's worth spending some time going through these and thinking about what are we multiplying together, what are we ending up with. So for example, over here, I've got two vectors, but I've dotted them. So what is this thing here, scalar or vector? Well, it's a dot product, so it's a scalar. So this thing is not a vector anymore. And yet, okay, I'm going to take the derivative, so I'm taking the derivative of something that's actually a scalar. So if I look at this form over here, do I end up with a scalar on the right-hand side? Because I would hope so. Well, I do. It's just two dot products added together. So take a little bit of time to just make your peace with these. And the heads up that I would give you is when you're working with equations involving vector functions as well as scalar functions, is to just slow right down. Maybe highlight the thing and then pause. Think about who's a vector, who's a scalar, how do you handle each of them? Because it's very easy to make mistakes. Okay. All right, so I'm going to give you an overview of this, but I think I will probably start next week by covering this again, because we've done a lot today, and I think brains are maybe full. Where are we going with this? Well, remember when I introduced the idea of our particle moving through space-time, I said that that was just kind of a useful mental image to have. But we can go more general, and it's in fact the more general that we need, where we are just thinking about vector functions of one variable. So I'm just not attaching any physical significance to the fact that I'm taking a number and I'm getting a vector out in some function. What I will keep thinking about is the curves in space that are made by this function. So really what we're thinking about in this section here is if you're working with a curve in 3D space, how do you work with that curve? So we're kind of, if it's helpful, think about it as the curve that a particle makes as it moves through time. So time is the thing that you're kind of, the independent variable that you're putting in, and the displacement is the thing that you're getting out. If that's helpful, think like that. But gradually get yourself thinking more generally, I'm putting a number in and I'm getting a vector out that is creating a curve as I change the input parameter. That's where we're headed. So something I wish that I'd been taught in undergrad, people kept telling me to parameterize curves, and I was like, what am I doing? I don't know what parameterization means. All parameterization means is we want to take some system that we want to describe. So maybe it's particle motion, any kind of physical system, so basically anything we do in physics, and we're going to describe it as a function of independent quantities. So most often what we do is we take time as our independent quantity and we describe the position in terms of time. We describe the velocity in terms of time. But there's nothing particularly special about time. It's just happens to be useful. But we can pick other independent things that we control in terms of we can put in what value of that parameter we're interested in. And what we get out of that is a description of something. So maybe a vector, you could get matrices, things like that. Yeah.
Theory of mind, what would be a dependent quantity we could not take as a parameter?
That is a good question. So if you think about a particle constrained to move in a circle, depending on where you're measuring it from, in some sense, its position is dependent on the time.
So you can't take its position.
So you can take it. It's tricky. It depends on, I suppose it depends on what you're measuring and how you're thinking about it. I will try and think of a better example. But these are the things that it's usually, the other way I think about it is, what are the things we want to measure? Like, I want to measure someone's height, based on the height, their height is kind of dependent on who they are. I'm measuring it, I don't know what it's going to be, but I measure it at a particular time. That's such a great expression. I'll think of something better. Okay. All right, where are we going with this? So this is for you to think about for next week, which pulls together a lot of what we've talked about and then introduces this new idea of parametrization. We've got a plane, and I've got a paraboloid, and they're intersecting in a parabola. So there is a curve in the shape of a parabola. And what I want you to do is think about how you might describe that curve using some parameter. What do I mean by that? I want an x of t, a y of t, and a z of t functions, so each of those is a function of t, so that when you put it together like this, over time, this position vector maps out that parabola. Okay, and I'll give you a hint, since I've already told you t is equal to x. This bit is easy. Okay, so I need some function of t that will tell me where y should go, and some function of t that will tell me where z will go. And then you will have parameterized your first curve. Go forth. Parameterize. Okay, but actually before then, I'm here for any questions. I realize we've just finished on time.